Welcome also to all of you on our superposition stage. And with that, we open in our Quantum Summit. And I already have my next dear speakers here on stage with me. And we will start with Heike Riel, Dr. Heike Riel, who is the head of science and technology and head of IBM Research Quantum Europe Quantum Europe and Africa. And she leads research agenda and operations of the Science and Technology Division with the goal of achieving scientific and technological breakthroughs in quantum computing. Heike, it's a big pleasure to have you here. Please, the stage is yours now.
Yeah, a very good morning to everyone, and thank you very much for showing up. It's really a great pleasure to be here and to talk about quantum computing. Quantum computing is the new kid on the block, as we say, if you look from the entire computing architecture. And I would like to take the next 10 minutes to lead you through the latest news and achievements and things which we are working on. And our mission at IBM is really to bring useful quantum computing to the world. And it's a journey we are on, and we have a lot of passion and motivation and have driven a lot over the last couple of years. And so one of the things, going back and looking back, actually, when I was in Yorktown, we have for the first time brought quantum computing via the cloud to the world. And in the last 7 years, a lot of things actually also have happened. And building a quantum computer, building a quantum system, has a lot of different individual pieces which we have to bring together. And so we are building a full stack, a full new computing architecture, as many of you also do. And it starts from the qubits. As a physicist, of course, I always start from the qubits. But this is by far not enough. We need also the quantum processor to scale the number of qubits, to all the components, the wiring, which we have to work on, the cryogenic platform, which also needs to scale, the control electronics. It's a cost factor. It also needs to miniaturize. The compiler, the software stack, the applications, the middleware, providing access through the cloud, and of course also the theory and the algorithms in order to provide value for industrial use cases, which we will talk later also about more. So in 2019, for the first time, we could demonstrate like a 27-qubit chip. And since then, every year, we have scaled up the number of qubits, have improved the quality and also the performance and the speed of how quantum computation works and is brought to our users. There are, of course, for all of these different quantum processor versions which you see here, whether it's a Falcon or the Hummingbird or the Eagle with 127 qubit, and also the Osprey, which we demonstrated last year with 433 qubits, for each individual one, there has to be new breakthroughs on the technology side to be done in order to demonstrate them. For the first one, it was how can we increase the yield of the qubits, that we can build and scale up the number of qubits in a single processor. For Hummingbird, it was the multiplexing readout. For Eagle, it was the first chip which was demonstrated above 100 qubits, where we had to go to a 3D architecture in order to wire and connect all the different qubits, which is above 100 qubits, no longer possible to do this in a plane. And this is actually shown, hopefully coming up here, in a movie. No, it's not coming up in a movie. So in actually what should have happened is now a movie where you see this 3D image into the package of the Osprey chip, which is a 433 qubit chip. And as I mentioned, you cannot wire all the different qubits together in one plane. You need to go 3D. You have like a layer with the qubits, you have a layer with the microwave resonators, and you have a layer for all the interconnects to be done and through substrate vias. From the silicon technology, we know how to build those things. But to do this for a quantum processor, where you work at 10 to 15 millikelvin, you have superconducting qubits, you need superconducting wires, you need the microwave hygiene to have the high quality of the qubits. It's much more difficult. And this was a big breakthrough in demonstration which we were able to make. So about 3 years ago, we have started to also disclose our roadmap in order to share with everyone of what is our path, where we want to be at which time. And this is also a big component how to build up an industry. Because when you look at the silicon industry back, there was always a roadmap which kind of predicted what is needed in the next 5 years. And this helped everyone, every player in the industry, to also contribute and to know what needs to happen in that time frame. So here you see what we have achieved so far. You see at the bottom the hardware components. You see here on top the different software layers. And when you look at the different software layers, then it's also clear from if you look at normal computing that we have to build up a software stack in order to allow quantum computing to be seamlessly used by computer scientists who don't know the details of the quantum physics. So when you look at the different software developer here, then we have kernel developers who need to understand the hardware. They will build circuits, they will build Qiskit runtime, dynamic circuits, and other features and capabilities which are then used by the algorithm developers to implement quantum algorithms. And we have built already quantum application modules where you can do machine learning, natural science use cases, and optimization. And then on top, there is a model developer who actually then should use these algorithms in order to solve real-world problems and use cases. So when we now look what is coming next, then you see we have big goals also for this year to be achieved. We want to build a qubit chip with more than 1,000 qubits, and also we'll start a new journey where we go into modularity. Because when you scale up quantum computing to then more than 100,000 qubits in 2033, which we announced in May, then you really have to build in also modularity. Modularity for quantum computing to scale and to make use of the chips which are available also today to increase the compute capacity and capability. Furthermore, in order to build also the quantum-centric supercomputing platform, we are working on the communication for quantum and also on the middleware for quantum, because as a user, you need to combine the architecture, the classical and the compute capabilities in one architecture to allow the tight and seamless integration of quantum and classical workflows. And this should result seamlessly. Furthermore, we want to provide capabilities like error mitigation and also circuit cutting techniques for the user to use the full capabilities of the quantum hardware which is available today. So then when you look here, we are also building up and increasing the capabilities on the software stack. Quantum serverless, I mentioned already. There are also intelligent orchestration, circuit cutting toolbox, and also the circuit libraries, which make it then easier for the model developers to use quantum software applications for machine learning, natural science, and optimization. So let me now focus a bit on the scaling of the quantum processors. So the first step this year for the Heron chip will be that we combine different quantum processors with classical links. And this allows you then to actually already parallelize jobs. So by this, you can make use already of certain circuit cutting techniques and increase the speed and the capabilities you have available. And next year, we would like to demonstrate for the first time then also that we combine quantum processors with a quantum link. And the quantum link, this one which is shown here, is on a short distance quantum link where you use like a 2-qubit gates to combine chips, and this combination of different processors appears then to the outside world, to the user, as one big quantum chip. Furthermore, we are also working on links, on longer distance links to combine different quantum processors. So this was on the hardware side, but if you look back, then there is a lot of innovation which is already happening also on the algorithm side. So there are techniques, the so-called circuit cutting and circuit knitting techniques used today, where you can, in principle, simply spoken, cut down your bigger problem into smaller problems and apply the today's available quantum processors for these smaller problems to create value. So one technique, for example, is embedding, where you make use of the quantum processor for the highly entangled part of your problem, and the other part you solve with a classical computer, and then you can connect these results together. Another one is entanglement forging, or also circuit cutting, which follow similar pathways. So one thing I didn't mention yet is errors, because we know in our current quantum computers we still have errors, and we have to deal with these errors. There is a way to use error correction. That's something the research community works very much on it to allow error correction in the future. But there is a path before. It's not a step function, but there's a continuous path to use and use quantum computers and increase their performance and capabilities. And one path is error mitigation. We have started in 2017 to actually apply error mitigation for the first time to small molecules, to lithium hydride in a 5-qubit chip. And this year in June, we have actually demonstrated that you can use error mitigation techniques where you understand the error and then you mitigate the error and create noise-free results, which really give you an advantage also in the future compared to classical compute. So for the first time here, we have cut it through the noise, so to speak, and we have demonstrated that a quantum computer can produce accurate expectation values, and this goes beyond what classical approximation techniques also can do. And this brings us closer to the utility and the advantage of quantum computing. So this is an example. I don't want to go too much into detail. I would encourage you to read through the paper. But we have really did, together with the Lawrence Livermore National Laboratory, which have used the HPC, we have looked at the trotterized time evolution of a 2D transverse field spin lattice and looked at the magnetization. And we have scaled up the number of qubits which were used for this problem. And when we have used 127 qubits, then the classical computer can no longer simulate 127 qubits. So brute force classical no longer works in these dimensions. So the quantum methods already today go beyond exact classical methods. And then, of course, you can use approximation methods on the high-performance computer. And there are, when we published the paper, like 3 weeks later, the classical world brought up new approximation methods. 3 new papers were published, and they actually demonstrated results which disagree about 20%, but in the same regime of what the 127 qubit error mitigated quantum computer could do. So I think it's really exciting times right now, because we are already now in a competition between HPC and quantum computers. And so we see the future now as something which is really making use of error mitigation techniques. And this allows us then, because when you look here towards working towards the quantum advantage, if you look at the simulation cost, a problem where the simulation cost exponentially increases at a classical computer, this is where you look in quantum computers for the advantage. Then you see here that if you do quantum error correction, we actually have a large overhead at the beginning, and then due to the different scaling at a certain point, it will allow you to have an advantage for quantum when you use quantum error correction. But meanwhile, we are in this regime today, and we are actually moved, I think, here, where we are competing now with the classical and error mitigation. And this is then the next step is to demonstrate here then the sweet spot, where we can achieve and create quantum advantage with error mitigation. And this is something where we all work towards. And I would like to encourage you to also participate, because early next year, we want to provide a compute capability, which is called 100 times 100. And the idea here is that we provide a compute capability of a width of 100, so 100 qubits, and a depth of 100. And this should be calculated within 1 day. so it's also in a very high speed. And now it's about the community to think about problems which you then can map to this compute capability, and hopefully this is where we then see also quantum advantage. And that's something which is also, we are expanding the compute capabilities, the number of quantum computers, we scale up the number of qubits. And you may have seen that we are also expanding the compute power which we have in Germany. So we have started in 2021 with the first quantum computer in Ehningen, which is fully used by Fraunhofer. And I think since then also a lot of boost has been given, and a lot of applications have been used in Germany. And we have committed now that we expand now and build really a quantum computing data center up in Germany. And this brings me actually to the next speaker. So, and back first to Natalia. Thank you very much.
Thank you very much. Thank you very much, Heike.